Okay, today we're going to talk about the fundamental theorem of algebra. In shorthand, the fundamental theorem of algebra states that for every polynomial equation with a degree higher than 0, at least one root exists. And how we can find the number of roots is by looking at the highest degree. Okay, so what does that mean? If we look at the polynomial y equals x cubed plus 6x squared minus 32, all we need to do is look at the highest degree. The highest degree is 3, so it's going to have 3 roots. Again, some may be real. They may actually be crossing the x-axis. Some of them might be imaginary, and we won't actually see those cross the x-axis. But it will have a total of 3. So if we look at a different example, what if we have it in a factored form? What if we have x minus 2 times x plus 3 times x squared minus 1? Again, if we were to factor this out, again, how many total x's do we have? We have 2, 3, 4, right? Okay, so you're going to have a total of 4 roots. Again, if we were to multiply that out, we don't need to multiply that out. I would have an x to the 4th equation. So because I would have x to the 4th equation, we have 4 roots. Might be easier for us to write it like this. This is actually to the 1st power, right? So this would be an x to the 4th equation, so 4 roots. Okay, what if we don't have the equation? What if we actually have the graph? Okay, we can also tell from the graph how many roots a polynomial might have by something called the multiplicity. So if I were to have a graph, and the equation actually crosses the x-axis, so if it crosses the x-axis, it has what we call multiplicity of 1. So again, let me title this. This is all based on multiplicity. If it only touches or bounces off, okay, so think about like a quadratic. So if it only touches, or I think it bounces off, this is what we call multiplicity 2. And if it kind of skids in an S shape, this would be a multiplicity. If it kind of skids, or I think of it as an S shape, it's going to be multiplicity 3. So how can we use this? If I have a sketch of a graph, so let's say I have a polynomial that, let's just say, comes up here, goes down here, crosses through here. So what if this is my polynomial? Well, I can actually write the equation for this polynomial based on where it crosses or touches the x-axis. So notice on the very left here, I have x minus 2. Well, inside think opposite, right? So it's going to be x plus 2. But notice that it's not crossing completely through it, that it's touching or bouncing off of that. So that's going to have a multiplicity of 2. Notice it crosses at the origin, so that's just going to be x to the 1st. Again, it completely crosses, so that's multiplicity 1. Notice here it goes through, let's say that's exactly 2. So since it's positive 2, inside think opposite, this is going to be parenthesis x minus 2, and that's going to be multiplicity 1 because it crosses. And at 3, again, inside think opposite, x minus 3, it bounces off or touches, it has multiplicity of 2. So notice here I can tell that my highest degree here will be 2, 3, 4, 5, 6, x to the 6th if we were to multiply it all out. But again, just from the graph and practicing finding multiplicities, at x equal 2, we'd have multiplicity 2 right here. This would be multiplicity 1. This would be multiplicity 1. This would be multiplicity 2. And then this would be the equation in factored form. Okay, so multiplicities definitely help you, A, find the equation of the graph, and B, lets you see how many roots you actually have. Okay, there's some other theorems that we can talk about in regards to polynomials. And the next one is called the conjugate root theorem. And the conjugate root theorem deals when we're taking the square root of certain values, and it states that, well, roots have to come in pairs. If a plus b, or a plus square root of b is a root, well then automatically I need to have the counterpoint, then a minus square root of b must be a root. And it goes vice versa. If a minus square root of b is a root, then automatically I have to have that plus. Because when I take square root, I need positive and negative. That works the same way with bi's. Okay, I could say that if I have a plus a bi, then automatically I'm going to need a minus a bi. Because again, how do we get I? I is found by taking the square root of a negative number. So how can we utilize this in a problem format? Find the degree with roots 2 minus 3i, 8, 2, and 4 plus square root of 2. Okay, well, anytime we have an I or a square root, we need additional roots. So I can't get 2 minus 3i without adding 2 plus 3i. I have to have the plus minus part because I'm taking the square root of a negative. And I can't get 4 plus square root 2 without having 4 minus square root of 2. So I need to add 2 additional. Now 8 and 2, those are just integers, so I don't need to add their counterparts. But since I'm adding 2 more, how many total roots am I going to have? I started with 4, I'm adding 2, so that is a total of 6. So again, let's do one more of this nature. What is the degree with roots 3 minus 2i, 5 halves, and square root 5. Again, we need to add anything that is an I or a square root with the opposite sign. So 3 minus 2i has to have 3 plus 2i. Square root of 5 has to have negative square root of 5. So how many total is this? 1, 2, 3, 4, 5. This is 5 roots total. So one last theorem, lots of different theorems with mathematics. It is called the rational root theorem. So rational root theorem states that we can find the possible roots with integer coefficients by taking factors of the constant divided by factors of the leading coefficient. So rational root theorem states that possible roots, in shorthand version, so again, how do we find possible roots? Our numerator, which we're going to call p, are actually going to be factors of the constant term. Okay, so your ending term. And your denominator q is going to be factors of the leading coefficient. So what does that mean? Find possible roots of 21x squared plus 29x plus 10. So we're first going to find factors. Of p. Well, what's our p value? Our p value is our constant term, so that's going to be 10. So what are factors of 10? Well, I could have plus or minus 1 and 10, right? Or I can have plus or minus 2 and 5. Well, now I need to find factors of my leading coefficient. Leading coefficient is the number in front of the highest exponent, so 21. So what are my ways to get 21? Plus or minus 1, plus or minus 21, plus or minus 3, plus or minus 7. So what we can do to find possible roots is we're going to take our first numerator and put it all over our denominator and keep going down the list. So possible roots. I can take my numerator of 1, so I can have 1 over 1, so that's just going to be 1. I can have 1 over 3, so that's going to be a third. I can have 1 over 7, so that's a seventh. I can have 1 over 21. So that is all with a numerator of 1, so let's go to the numerator of 2. I can have 2 over 1, so that's just 2. I can have 2 over 3. I can have 2 over 7. I can have 2 over 21. Again, that is it for numerator of 2, so let's go to 5. I can have 5 over 1. I can have 5 over 3. I can have 5 over 7. I can have 5 over 21. So that's it for 5. Lastly, I can do 10. I can do 10 over 1, which is 10. I can do 10 over 3. I can do 10 over 7. And I can do 10 over 21. Now, based on this polynomial, our highest degree is 2. Only 2 of these are actual roots, or i.e. x-intercepts, but it can only come from these possibilities. Okay, so rational root theorem to find possible roots. Take factors of your constant divided by factors of your leading coefficient.